Okay, now we're going to switch to the Hottel Lecture. And it gives me great pleasure to introduce this year's lecturer, Professor Heinz Pitsch. Heinz is a professor at RWTH in Aachen, Germany. And he's a director of the Institute for Combustion Technology there. And he's been there since 2010. Many of you would know that Heinz was the student of the late Norbert Peters, and he finished his degree, his PhD, in 1998. Heinz did a postdoc at University of California, San Diego, at Stanford, and then he had a stint as an assistant and associate professor at Stanford from 2003 to 2013. Heinz has many interests, and he has contributed seminal works in a lot of fields, including combustion theory, combustion chemistry, turbulence, multi-phase flows, and much more. And much of it is also tailored towards combustion systems, including engines and so on. Heinz has published widely and well-cited, and currently is the chair of the German section of the Combustion Institute and the co-editor-in-chief of the Journal of Application in Energy and Combustion Science. He's a fellow of the American Physical Society and, of course, of the Combustion Institute, and has received many prestigious awards, including the Advanced Grants for European Research Council and the International Award of the Japanese Combustion Society. Please join me in welcoming Professor Heinz Pitsch to the stage.
Yeah, thanks, Bassam, for the nice words. Good morning, everyone. Thanks to the program chairs for inviting me to give this lecture. This is really a great honor for me. Thanks also to the local organizing team for hosting us here in such a nice place. So the title of my presentation here is Transition to Sustainable Combustion, Hydrogen and Carbon-Based Future Fuels and Methods for Dealing with Their Challenges. And I will start by saying some of the obvious things that have already been pointed out. Also, do I have the right one? No? No. This is not working. Yeah, the clicker here to get to the next slide. Okay. Ah, here we go. Okay. Well, was this you or was this me? No? Was it you? Okay. Yeah. I mean, it worked for like a second, right? It worked for like a second, advance one slide. So yesterday I came here, I said to the chairs, I want to test all this out because in these big presentations very often are a disaster. But everything worked great, so you're lucky. But that was yesterday. Yeah, so bringing up the presentation again, I was actually hoping we could start 5 minutes early because I have too many slides as always. And now I'm actually losing 5 minutes in the beginning. Maybe I should just start talking before you see the slide. So I wanted to start really saying some of the obvious things which have already been mentioned, have been mentioned also by the Vice Rector, is that we know the temperature is rising in the world. We know this has disastrous consequences, really disastrous in the actual, yeah. Oh, I have so many animations that it will give you like every second. Okay, now it works. No? Yeah, okay. Okay, I'll try to do my best. So I mentioned temperatures rising. We know it will have disastrous consequences. We have put a lot of measures in place to mitigate these problems, very ambitious measures. We also know global warming is mostly caused by CO2 emissions by combustion of fossil fuels. But what I want to say is that combustion is not the problem. Combustion is a technology that by itself is not harmful. Okay. So combustion by itself is not harmful. Combustion is also a technology that brings a lot of benefit to our society. And the problem really are the fuels. Now, fuels are the largest commodity in the world. And about 75% of all the total energy demand today is provided by combustion of fossil fuels, which brings us, each single person here in this room, to emit on average 12 kilogram per person per day of CO2. This is a huge number. If you think of this room, if you think of the world population, and it makes it clear how almost impossible it seems to make a change, a transition to something that's totally different. So that's very challenging. So the World Energy Outlook brings out these projections for different scenarios. The stated policies scenario assumes that we stick to what's already in policies that are already in place. Announced pledges assumes that we do what we already promised, and the net zero emission scenario should bring us to net zero emissions in 2050 and also limit global warming to 1.5 degrees. And you see here the total energy consumption in these years, which means this has to go down, and if you want to reach this ambitious goal. And also you see here the lines, they show the relative fractions here of oil, natural gas and coal, which are declining, and then of electricity, modern renewables, which is mostly biomass or bioenergy, and also hydrogen. And if we look at this, so the more right you go here, the more ambitious the goals get, and the less you have of actual fuels. But even in this most optimistic scenario, we see that by 2050, still 40% of the total energy consumption is based on fuels, and this will mostly be converted by thermochemical energy conversion. And half of that is in bio and synthetic fuels, and this is the topic of this presentation. So we can, as an example, we can look at the energy demand in industry, which today accounts for about 40% of the total energy demand. It's used mostly in the energy-intensive industry, shown up here, for producing high-temperature heat, which is very difficult to electrify. And so if we look at the projection here, first of all, it says, in the net zero emission scenario, it says that the energy demand industry is not going to change very much by 2050, which actually brings up its share to the total demand to close to 50%. And if we look at the details then, we see that even here in the net zero emission scenario, by 2050, there's a lot of electricity, but there's still a lot of coal, oil, natural gas, with and without carbon capture, hydrogen, bioenergy, so that the total of combustion of fuels still contributes to more than 30%. And that's an interesting number, because it shows that in all of these scenarios, combustion will still play a role, even in a scenario where we have reached net zero emissions. So that's important. Now we know that one of the big challenges is that renewable energy is not always present when and where we need it, which means there's a need for energy transport and storage. And that's best done with chemical energy carriers because of their good energy density and specific energy. And so you see here a bunch of values here for present fuels, hydrogen-based fuels, metal fuels, and also carbon-based e-fuels, biofuels, and what we call biohybrid fuels. And you see most of them are doing pretty well in this metric. So these fuels, some of them can be utilized here in fuel cells to produce electrical power. All of these can be used in thermochemical energy conversion, which is combustion, to produce mechanical and electrical power and also produce heat. And combustion has a number of really good advantages. One is that combustion is possible for both power and high temperature heat production. It's possible to be used in all sectors. It is a proven technology, so we kind of know how to do it. It's more fuel flexible than electrochemistry-based processes, and also to some degree, combustion is a technology that allows for a continuous energy transition by gradually replacing present fuels with renewable fuels, which is discussed in more detail here in this paper by Dreitzler and others. So the topic here is combustion of hydrogen and carbon-based fuels. Now, new fuels provide challenges, especially if they have totally different combustion properties than what we are used to, and which means that if we want to manage the energy transition, computational design has to play a more and more important role. At computational design, for instance, here joint optimization of combustion devices and their operation is very important, and an example is shown here on the right for an aero engine. Now, the problem is, for such an optimization, we need accurate models, and we know because combustion is very complex, it's highly nonlinear, it's very, very difficult to model combustion with good accuracy. We know that simulations, for example, they come with typically with large uncertainties. So model improvements and proper validation are very important, and further improvements in modeling, really maybe with step changes, they are urgently needed. So how do we do this? How do we get to the next level of models? And here I want to make 2 points. The first is that because of the complexity of combustion, model validation is really very, very difficult. So typically we are interested in simulations of some complex combustion system, but for that system we don't have any data, or we don't have much data. So we resort to lab-scale experiments, but for lab-scale experiments, very often they are not quite at the conditions we're interested in, and also we don't have enough data to really inform the models for how they have to be improved. From DNS, we have tons of data, all we need, but DNS are usually very far from, in terms of operating conditions, from the reality. And so, you know, there's an issue at all of these levels. So the point that I've been trying to make for actually quite some time is that we need to coordinate this validation efforts better. We need to find the same physics in all of these, at all of these levels. We need to design jointly the experiments and the DNS. We need to use them jointly in the validation exercise, and that's something that is not easy to do, because one student typically can do a validation simulation of one of these, and then the PhD is over. So you cannot look at all of this. So we need to make it more easy for people to actually also do simulations like this more frequently. And so this is something I think is really important, and we're not doing this today. We need to find out how to do this. The second here is that we keep doing improvements of models, making models more accurate and also determining uncertainties better. But one of the issues is that many of the combustion models we have, they've reached a certain level of maturity, so you're kind of hitting a wall, and it's very difficult to go beyond this. Further advancements become harder and harder, and so that's an opportunity to look at new approaches, and one of the relatively new approaches here, let's say, is machine learning, and so we need to embrace machine learning better in our modeling, not in a way where it replaces physics-based modeling, but in a way where we use physics-based modeling for what we know how to do, and then for what we don't know, we enhance these by machine learning approaches. This is, again, something that you will hear a lot about. Matthias will give a talk tomorrow about machine learning. But for example, the fluid mechanics community is way ahead of us, and we need to do this better and look at the different approaches. So then, before I give you an overview of what's coming, here a little cartoon. So this is an energy policy meeting, and the chair of the meeting says, before I ask the question, can anyone anticipate the answer? And you see this guy here is really wants to say something, so he yells hydrogen. And then there's the guy here in the back, and he yells artificial intelligence. So these are the very hyped topics you read about every day. I mean, at least in Germany in the newspaper, I read about these two every day. And you're lucky, today I'm going to talk about both of these. So the hypotheses that are the guide for what's coming is that first, understanding, describing, and designing future fuels is essential for the energy transition. Second, the transition to new fuels requires also a transition to new methods. And so what I want to do here is I want to discuss different aspects of future fuels and also give examples for how we use machine learning in assisting these efforts. Now, specifically, I will talk about hydrogen-based fuels, hydrogen ammonia, about the chemistry, intrinsic flame instabilities, which turn out to be really important, and then also about physics and machine learning-based models for how we deal with these. Now, the paper also has a chapter on carbon-based fuels about biohybrid fuels, how we define these as a synergy of e-fuels and biofuels to extend the molecular design space of possible fuels, how quantitative structure property relationships are built using machine learning techniques, how we do fuel design new fuels that have improved properties in terms of efficiency and pollutant formation for internal combustion engine, and also how we use machine learning-based methods for automatic mechanism development. So I'm not going to talk about here today because of the interest of time, but if you're interested in this, have a look at the paper. There's a lot of information. So, talking about machine learning, talking about artificial intelligence. When I put this talk together, I came to this point, I typed the word hydrogen, and immediately PowerPoint, the artificial intelligence of PowerPoint, starts to suggest fancy backgrounds. And I thought, okay, that's good, lighten it up a little bit, add a fancy background. This here's the first one that came. And I was thinking, yes, it looks very fancy, but there's something wrong. So I kept this here as a warning for, yes, we do use artificial intelligence, but if you do, you really got to be careful with what it suggests. Okay, so this same slide's a little more traditional. From now on, you will not see any fancy backgrounds anymore. So I start with hydrogen-based fuels. They're really very different. Hydrogen has very low energy density. We know this is bad for transport, mobility applications. It has a higher adiabatic flame temperature compared with methane, which might promote NOx. More importantly, it has a really high flame speed, laminar flame speed here compared to methane, which of course influences all kinds of stability issues, but also promotes wall heat losses in engines and is a challenge for fuel flexibility. Also very important is hydrogen has a very high diffusivity, which leads to a low Lewis number defined here as the ratio of thermal energy diffusivity, which is heat transfer, to mass diffusion of a certain species. Hydrogen has a Lewis number of roughly 0.3, which means it diffuses 3 times faster than thermal energy. And that is very important because it causes here these instabilities that you see here in this animation. Ammonia, on the other hand, can be liquefied under non-extreme conditions. That's very good for transport and storage. It has, because of the nitrogen in the molecule, it has tendency to form nitrogen oxides, and also it has a very low laminar burning velocity. Why it's often suggested to use it in blends with hydrogen, but I'm not going to talk about this today. So why does hydrogen burn so fast? This is an experiment that we run in our lab here in the group of Joachim Bickmann. We have a spherical chamber. We fill it with a fuel oxidizer mixture. We put a spark in the center, and then we see with a Schlieren system how the flame evolves. And if you compare now hydrogen with methane, you see immediately hydrogen is much, much faster. And this has 3 reasons. The reason number one is, as already said, it has a much higher unstretched laminar flame speed. Second, flame stretch and curvature actually impact also the flame speed. And for a spherical flame like this means hydrogen burns faster, and for methane, it means it burns slower. So that's the second reason. And the third is, you see this here in the video, the lean hydrogen flames, they develop these flame instabilities on the surface, and that also really tremendously impacts the flame speed. So we can now look at these three one by one. Let's start with the unstretched laminar burning velocity, which for hydrogen at stoichiometric conditions is about 6 times higher than for methane. And that could have 3 reasons. The first is transport. Obviously, if the Lewis number is if the diffusivity is very large, it suggests that the flame would be faster. Thermodynamics, second reason, we know that adiabatic flame temperature has an exponential impact on the flame speed. And then, of course, chemistry and radical balance, they could be different in these for these different fuels. Now we can test these here one by one. Transport, to test the transport, we can set the Lewis number as equal to 1. To test thermodynamics, we can adjust the flame temperatures such that in the hydrogen flames, they have the same adiabatic flame temperature as in the methane flame by artificially adjusting the nitrogen heat capacity as suggested by Professor Faravelli and co-workers. And we see if we do that, then especially here for lean, for stoichiometric and lean flames, it really doesn't make all that much of a difference, which means chemistry must be the main reason why this burns so fast. And to look at the chemistry, we can consider the fuel consumption pathways. So this here is for methane, fuel consumption pathway. Then we can introduce steady state assumptions for all the intermediates, except for hydrogen. And then we end up here with this net reaction, as also shown here in the 4-step Peters-Williams mechanism. And it shows that if you consume one methane molecule, you have to consume also 2 hydrogen radicals. And that's interesting, because that means methane actually is a flame inhibitor. Okay, and we know that in premixed flames, the action really starts only once all the methane is gone. We do the same for hydrogen. You see here that hydrogen consumption actually produces radicals, so it's exactly the opposite. Hydrogen consumption makes it fast, while methane consumption makes the flame slow, and so this is the main reason why this hydrogen flame is so fast. Now we can ask the same question for ammonia. Why is ammonia so slow? And that's a lot more difficult because of 2 reasons. First of all, there's not one single consumption pathway, but there are several competing pathways. But secondly, also, there's a lot more uncertainty in the chemistry. So for the second point here, we did an assessment of 16 of the most recent mechanisms for ammonia. And from this, then, we have a lot of data. And from this, we chose the NUIG model here for this analysis. So here, we're looking at a stoichiometric premixed flame at standard conditions. And ammonia is, first of all, consumed in this net reaction, forming the NH radical. This is still radical neutral, because NH is a diradical, so it compensates here for these 2 H on the left side. So the key here in the chemistry is really the consumption of this NH radical. And there are 3 pathways that consume this. And what's interesting here, so the fractions of the consumption are given here in the parentheses. And so if we look at the net reactions, then these are the net reactions. And if we look at the radical balance, we see the second one here actually consumes per ammonia molecule 2 radicals. That's exactly the same as for methane. But now the first one, it consumes only 1 radical. So that would actually make it faster than methane. But the third here, you see, considering that the NO consumption eats up 1 more radical, this takes 4 radicals per molecule. And so that's highly chain terminating. And what's interesting here is that although this is the slowest of these 3 reactions, this is the most important, really determining the dynamics. And we can test this here by starting out with the full mechanism, which gives us a flame speed of 6.6 centimeter per second, and now gradually introducing changes until we reach the methane flame speed. And so the first thing here we do, again, we adjust the temperature. That already increases the flame speed by a substantial amount. Then we keep only these three reactions as consumption reactions for NH, which eliminates a few more chain terminating reactions. Then we neglect this very important or side chain, very chain terminating, I should say, side chain here of NH2, also increases here by a little bit. And now we neglect only this reaction. Again, this is the slowest of the three, but highly chain terminating, and this almost doubles the flame speed now, okay? So all in all, ammonia burns so slow. Most of these here are really the radical balance, and then there's also some contribution from the lower temperature. Okay, so that's the laminar flame speed. Now we can look at stretch. Flame stretch is defined as the flame area rate of change that is caused here by curvature or strain. It's shown here on the right. If you have a flame with a positive curvature, you let it burn, then the area will increase. Similarly, if you stretch, if you have tangential strain on the flame, it will be stretched, and it also increases the flame surface. So these affect the flame speed, and there have been several classical theoretical works that look at the effect of stretch on flame speed. And this linear relation here was suggested, where the Markstein length appears here as a coefficient. Now, when we measure flame speeds, we spark the flame. The small flame kernel has high curvature, high stretch, and then we observe how it grows and the stretch decreases. And then finally, we take the data and extrapolate it to zero stretch, an infinitely large flame, to obtain the laminar flame speed. And you see here that the Markstein length is actually the slope or the negative slope of this line. And so the slope here is negative, which means the Markstein length is positive. And you see that a stretched flame burns, stretched methane flame burns more slowly than an unstretched flame. For hydrogen, it's exactly the opposite. You see the Markstein length now becomes negative, and the stretched flame burns faster than the unstretched flame. That, you know, I mean, you could look at the numbers here, and you see that makes only 20%. 20% is not very much, and it looks like, yes, we can almost neglect this. But the fact is that this difference, stretch effect, actually causes the flame instability, and that will have a quantitatively a huge effect, so it's an important effect to consider. So then we want to look at instabilities in lean hydrogen flames. We'll see that they have a really strong impact on consumption speed. It actually has there are actually two effects. One is the hydrodynamic or the Darius-Landau instability. The second is the thermodiffusive instability. And the second here is much more important than the first. Now, one thing that one should point out is these instabilities have nothing to do with thermoacoustic instabilities, which depend on the system, pressure waves, and so on. There are no pressure waves here. These are not dependent on the system. They are intrinsic to the flame, which is why we call them sometimes intrinsic instabilities. So here we want to look at quantitatively how important these are. We want to look at what causes these and also how we model these. So from a mathematical equation point of view, it's very easy to understand what causes these. We start out here with a flat flame. It's burned on top, unburned on the bottom. The flame propagates from top to bottom. Then we add a little perturbation, so we have positive and negative curvature regions. And then we just look at that equation that we just had, where now, considering that Markstein length here for hydrogen is negative, a positive curvature actually makes the flame speed faster, and for negative curvature, the opposite is the case. So an initial perturbation will grow in time, and so that's an instability. From a physical point of view, differential diffusion between hydrogen and thermal energy causes the following. The hydrogen, so in a positive curvature region like here, the hydrogen diffuses into the flame with a very high flux, and it brings chemical energy to focuses chemical energy to one point, where it's converted through combustion to thermal energy, but that thermal energy cannot diffuse as fast out anymore. So you locally create regions of high enthalpy, which causes high temperature, and also increases then the burning velocity. And then similarly, preferential diffusion between hydrogen and other species, for example, oxygen, is similar. Hydrogen focuses on this one point with a very high flux, oxygen with a smaller flux, and so you locally create richer regions, and that also increases the burning velocity. So both differential and preferential diffusion, they contribute to promote the instability, and one interesting question is, which one's more important, okay? So, before we answer that question, we look a little more in the theory. So we start out looking at the dynamics, at how fast the instability grows. And we do this by looking at the linear regime, which means in a regime where the perturbation grows, but it's still very, very small. So we do this with detailed simulations here. We start with a flat flame. We add a very small perturbation at a certain wave number or certain wavelength, and then we let it start a simulation. And we start a simulation and we see what's going on. So in this case, the instability, the perturbation grows. We fit this then to an exponential growth, and which gives us a growth rate omega, which then we can do for all possible wave numbers, and we get a dispersion relation here, which is the growth rate as function of the non-dimensional wave number. Now, this is the simulation that's shown here for hydrogen air flame, lean at equivalence ratio of 0.4, otherwise ambient conditions. So we'll call this the reference case, and I will refer to this reference case, equivalence ratio of 0.4, over and over. You see here, when omega is positive, it is unstable. When omega is negative, an initial perturbation will be damped, and the critical wavelength here is about 3 times the flame thickness for this case, which is very important information. For example, when we do LES modeling, the largest the maximum growth is at about 6 times the laminar flame speed. So there have been a lot of theories, or several theories, that describe this instability or the dispersion relation. You see here one by Matalon, one by Sivashinsky. They're both based on different assumptions. And you see the analytic form here of the Matalon's model here on the right. It has 2 terms. The first one is this here. It's actually linear with the wave number, as shown here. It's always positive, and it only depends on the density ratio. It does not depend on chemistry. It does not depend on diffusion or Lewis number. So this is the characterizes the Darius-Landau or hydrodynamic instability. And then the second term here, that actually characterizes the thermodiffusive instability. You see the Lewis number. When the Lewis number is large, this term here will be negative. It will stabilize the flame. When the Lewis number is small, then this is negative, it is positive, and it also contributes to the instability. Now, if you look at the quantitative comparison of the theories with the simulation result, you see it's not very accurate, but that's not really important. And we can actually explain why this is. What's more important is that the theory really tells us what parameters govern this problem. That's a very, very powerful result. So we see here that it's the density ratio, the Zeldovich number, which is just a non-dimensional activation energy of a one-step global reaction, and the effective Lewis number, which for lean hydrogen flames is just the Lewis number of hydrogen. These are the 3 parameters that govern the problem, and that's it. So we can compute these dispersion relations for many different conditions, where different combinations of pressure, temperature, and equivalence ratio. And without going into details, what we see is that the instability gets stronger when the equivalence ratio goes down, when the temperature goes down, or when the pressure goes up. And what's also interesting is that now we can try, because the theory told us we have only 3 parameters, we can try to fit the results that we have with these 3 parameters. And you see we get this is a regression line here, we get an almost perfect fit. And that's, again, is important, not because, the fit now is accurate. That's not the point. The point is that the quality of the fit shows that these are really the only governing parameters. And that is really interesting, because the Zeldovich number is based on the activation of a one-step global reaction. There's no more information about the chemistry than just one activation energy. And that means all the instability, at least in the linear regime, it can be described by a one-step global reaction. That's very, very important for modeling, and I'll show you later that's the only reason why the models that we have, they kind of work. So we can now also look at the instability in the nonlinear regime. So we start again with the same configuration, burned on top, unburned on the bottom. We add a perturbation, and now we start a simulation, detailed chemistry. Here's again the reference point, and we see how the instability develops past the linear regime. And what you see here, you get a lot of variations here of temperature in the burnt gases, even though this was fully pre-mixed. And you see that this becomes totally chaotic, and ultimately it reaches a steady state. Now, how fast this burns, we can quantify by the consumption speed, which tells us how fast is the fuel burnt compared or consumed compared to an unstretched premixed flat flame, and that can be decomposed in an area increase, which you obviously see here, and also in an increase of the local flame speed. You know, how fast does the local flame speed compared with the unstretched laminar value, and that ratio is what we call the stretch factor. So in this particular case, the consumption speed is 4 times faster than the laminar case, than the flat flame, which is because it's twice the area, and also the stretch factor is 2, which means locally this flame burns twice as fast as the unstretched flame, even though this is still a laminar case, no turbulence here. Now we can also do this for many different cases. We actually use the same combinations here we did before. Again, we can fit this with the 3 parameters. And also here we see we get a good correlation, which again shows that these are the only parameters that govern also the nonlinear regime. And also it means that also here, the details of chemical kinetics are not very important. And again, that's important. Now, other people have also looked at such scalings. Here, Ried et al., they actually have developed the scaling with only 1 parameter, and they get a good regression here for the stretch factor. What's interesting about this is that this parameter, Zeldovich number over Peckley number, it can be easily computed here from 1D flame simulations. Another scaling was given here by Howarth and Aspden, and they here, interestingly, they used the coefficient that appears in the theory, in Matalon's theory, omega-2 parameter, as the only coefficient, and also they get an excellent scaling here, shown in the black line. Now, they also looked at cases where the pressure is very high, that the temperatures are low, or the equivalence ratio is very small at the same time, and then what they found is there's a different scaling, and that's the case when additional recombination reactions here become important, and then the whole thing is not only described with 1-step global chemistry. So for some conditions, the chemistry actually starts to play a role. Now, before we turn to the turbulent cases, we can look at the question I posed earlier. Which one is more important, differential diffusion between fuel and thermal energy, which leads to locally increased enthalpy, or preferential diffusion between different species, which leads to locally increased equivalence ratio? So I'm not going to ask you to raise your hand, but take a pick now, and then I'll give you the answer in a second. So we do this again by doing detailed simulations, and you see here the reference case again. You see here also the numbers for the consumption speed. You see the number here for the stretch factor. Okay, so that's the reference. Now we can do a simulation where we set all the Lewis numbers equal to 1, so there's no differential diffusion, no preferential diffusion, and then you see the stretch factor is 1. There's only a very small increase in consumption speed because of the hydrodynamic instability, but it's roughly the same. Now, this is a trick I stole from Andy Aspden. He did this for a turbulent flame. Now we set all the Lewis numbers equal to the Lewis number of hydrogen, which means we still have differential diffusion because the Lewis number of hydrogen is 0.3, but we don't have any preferential diffusion because all the Lewis numbers are the same. And you see we get almost the same result as for the reference case. Okay, so this seems to be do part of the trick. And then this is my own trick. Now we do the opposite. Now we divide all the Lewis numbers by the hydrogen Lewis number, which means now the hydrogen Lewis number is equal to 1, which means we suppress differential diffusion, but the ratio of all other Lewis numbers is still the same. And so preferential diffusion is still there. And now you see we get almost the same result as for the Lewis number equal 1 case, so which means differential diffusion is very important. Preferential diffusion is not all that important, but most of the models today, they're more based on the preferential diffusion thinking. Okay, again, important result for modeling. So now we look at turbulent flames. That's really interesting because, and I might be done in 2 seconds, because for turbulent flows, we know that molecular effects are usually overshadowed by the turbulence. They're usually not very important. And most cases, we actually neglect molecular transport effects altogether when we model turbulent flows. So because the instability is a molecular effect, it could mean that it's not important at all in turbulent flows. But we'll see the opposite is the case. So to look at this, we did simulations here of hydrogen air slot jet flames. Again, for the reference case, we did 2 simulations. One where we set the Lewis numbers equal to 1. So this suppresses the instability. We call this the stable case. And one here with detailed transport, I call this the instability case. And I mean, what you see, first of all, if you just look at the scale, is that this flame here is 3 times shorter, which means the flame burns 3 times faster. So it's a really, really strong effect that we still see here in this turbulent flame. By the way, Reynolds number is 11,000, so it's not 0. I mean, this is a decent turbulent jet. What we also see is that we locally look at the mixture fraction or the equivalence ratio. We see that even though the mixture is fully pre-mixed, we see that in the flame, we get locally very much richer regions and much linear regions sticking into the unburned gases. That's a characteristic of the instability. You look at the temperature, we see we get very strongly super adiabatic temperatures, 400 degrees actually higher than the adiabatic flame temperature. And we look at the PDF of the temperature, you see for the turbulent case now, this is even much stronger than the laminar case. And so if you look at the stretch factor, we saw that it is in this case here, the stable case equal to 1. We saw earlier in the laminar case, it was 2, and now in the turbulent case equal to 5. So there's a very strong synergistic effect between the instability and the turbulence. The turbulence creates more curvature, and the curvature actually promotes the instability. So the instability gets much stronger. And these are really, really large values, and they must be important for engine design. Now, when I ask the question, what happens if I go to really high, if I make the turbulence stronger, so that at some point the instability must go away. So stronger means the Karlovitz number gets higher, and here Andy Aspen and Mark Day, they have looked at this actually many years ago. They did a simulation at low Karlovitz number and a super high Karlovitz number. For the low Karlovitz number, they see a lot of variations of the equivalence ratio and strongly super adiabatic temperatures. For the high Karlovitz number here, no variation in the equivalence ratio and also no super adiabatic temperature. So if you crank it up enough, it seems like, at least for this case, the instability then disappears. But what we know is that, so this is isotropic turbulence in the box. If we know that if you want to stabilize a flame, a premixed flame at super high Karlovitz number, is very difficult if you don't want to blow it out or get extinction and so on. So we did a series here of jet flames for increasing Karlovitz number here. But what we see here also is that the highest Karlovitz number, you get less of these finger structures, you get smaller super adiabatic temperature, you get smaller consumption speed, only here at the highest Karlovitz number. So the effect of the instability weakens. But what's interesting is, although the consumption speed gets smaller, you see here the stretch factor, it still keeps increasing, okay? And so the reason here is just that the area gets smaller, which you can also kind of see. So that's actually a talk here at the Combustion Symposium. If you want the details, you can check that out. So if I want to summarize the intrinsic instabilities, we saw that they substantially increase consumption speeds. We saw that they don't really depend on details of chemical kinetics, except maybe for some extreme cases. We saw that differential diffusion is much more important than preferential diffusion. And we also saw that these effects are strongly increased in turbulent flows. And now, if we want to model this, the question is, what are the challenges for modeling? The first challenge is that now molecular transport effects, they're very, very important. Usually, as I said, we neglect these. And so at least differential diffusion now needs to be considered. Secondly, and that's even more difficult, instabilities always grow from small to large scales. And what this means is a growth like this is not described by classical turbulence theory. So it's very difficult to model. This is like Rayleigh-Taylor instability or Risch-Meyer-Meshkov instability in turbulent flows. People have looked at this for a long time, but I don't think we have any good models to describe these in turbulent flows. So this is a really challenging problem. The other thing that was pointed out here by La Pena and Creta is that the most unstable modes that I mentioned earlier, they are actually mostly on the subfilter scale in LES, and so, we don't see these. They must be modeled entirely. And then another issue is that in LES, the instability needs to grow from the smaller scales. But the smaller scales are not resolved in LES. They are just numerical garbage. And so that also is not very good for accurate simulations then. Okay, so these 3 points I'm going to try to address. And so we start out here looking at models. This is, we look at the flamelet model. And I'm going to start out looking just at the case for Lewis number equal 1, no instability yet. This is the joint PDF of the source term and the progress variable. And you see here in red is the conditional mean, which describes the PDF quite well. And then in black is just an unstretched premix flames at the nominal conditions. And you see that's an almost perfect model. So that's very good. If we look at this data for the case with the instability, now we see the chemical source terms all over the place, and this flame here, it does not model this well. So now we need additional descriptors, and that's shown here. So now what happens if we look at 2 variables? This shows the chemical source term as function of 2 variables, a progress variable and a mixture fraction, could be something else. And now you see this data is almost collapses almost perfectly onto a 2-dimensional manifold. So the chemical state is well represented by 2 variables. Now people have realized this long time ago. A model here was actually proposed by Rob Bastians a long time ago. Here he proposed using a progress variable and a temperature. That was actually during his time when he was at Stanford, and he introduced me at the time to this subject. So thanks, Rob, if you're here, for doing this. And another example here is a model by Regler. They used a progress variable and then a mixture fraction, which is just a coupling function between 2 reactive scalars. You derive a transport equation for this. It looks like this. It has no chemical source term, and it just tells you what's the local equivalence ratio. But it has 2 terms which need closure. But what's nice about this is these 2 terms, they're almost linear, so modeling should be relatively simple. So then this model was tested a priori using the DNS data by Berger et al. And this shows the error of different model variants. And you see here one particular model variant. I'm not going into details. It has a really low error. And then they tested this also here for a posteriori, doing an actual LES of this DNS case. You see here on the left, this is the hydrogen mass flux as function of distance from the nozzle, which gives you an idea for the flame length. And on the right here, you see the DNS and the different models. And this is the model with only 1 variable, 1 parameter, and that should not work, and it does not work. This here is finite rate chemistry. Without any closure is the green line here, also way over predicts the flame length. These are the models, different flavors, and they are actually much better, but still there's some gap here. What causes this gap? The 2 issues I mentioned earlier. First of all, the instability growth is at the subfilter level, and that is not considered here yet. And secondly, numerical errors at the grid level prevent initiation of the instability. And that's a really challenging problem, and this is the place where machine learning could come in. Machine learning is what we want to use here now to tackle these 2 issues. We start here again with the regular model with these 2 variables. We only look at the mixture fraction equation. This equation has 3 terms that need modeling. Here, for example, the subfilter scalar flux, for which we would usually use a gradient transport model, but the gradient transport model doesn't know anything about the instability, so that's must be a bad model. The alternative is to evaluate this term from its definition. That's shown here, but the problem of this, of course, is that this term we cannot evaluate from the LES. This is what poses the modeling problem in the first place. So here the idea is we start with the LES field. We use machine learning to super resolve the LES to a DNS-like resolution, and then from the DNS, then we can evaluate all these terms and close the problem. And that's for this for this super resolution, we use a technique, it's called here super resolution generative adversarial networks, and that was originally proposed by Fukami for non-reactive flows and by Bode for reactive flows. And this is how this works. This is actually an intriguing concept in a way. We call this physics-informed enhanced super-resolution generative adversarial network long-term, but all the rest here, this is what the computer scientists call their method. Physics-informed here just means that during the training, we enforce continuity to be satisfied. So this is how this works. We start with a DNS database. Each field is then filtered to an LES resolution, and the generator is trained to give us back the DNS resolution. Okay, so that's what the generator does. The generator is a very deep convolutional neural network. We also train a second deep neural network, which is called the discriminator. And the discriminator, the only task is, it's supposed to tell you for an input field, is this a real DNS field or is it a fake DNS field that I got from the generator? So we train it to be able to discriminate these, and then comes the trick, which is the adversarial training. Then we let the two play against each other. So the generator makes these DNS-like fake images and feeds them into the discriminator, and the discriminator, so it tries to trick the discriminator, but the discriminator tries to find out. And how good the discriminator is actually fed back in the further training of the discriminator. So this will get better and better in identifying fake images. And it's also fed back in the adversarial, so-called adversarial training to the generator, which gets better and better in tricking the discriminator. So both get better all the time, and it goes to infinite artificial intelligence. Okay, maybe not quite. But what's interesting about this is that, first of all, these networks, they compete, they improve each other, and then also the discriminator is now a very powerful tool because we can use it for an unsupervised training later on. So this is how the unsupervised training works. I think I'm running out of time, so I'll skip this. But the point here is that now we can use real LES fields in the training, which are contaminated by numerical errors, and the generator learns to also compensate for the numerical errors. This shows how well this works, and let me just show you the final result here with the supervised training. This is an energy spectrum here for isotropic turbulence. This is the velocity gradient PDF. In red is the DNS, this is the recovered DNS, and you see the match is almost perfect. And it turns out that the unsupervised training particularly helps to improve the predictions at the small scales. And that's very important because that's exactly what we need to predict the instability. So here we test this on a premixed hydrogen flame. You see here the DNS. You see this is a filtered field at 16 times the DNS resolution, and you see that here these features that we have that characterize the instability, they actually are completely washed away. And if we super resolve this now, not all the way to the DNS, but only by a factor of 4, we see that these features here appear again. And you see here even this hole, which completely disappeared here, somehow this method captures this hole again, which means we can use this now in an LES, which we haven't done yet. Okay, so then let me conclude. I try to make the point that combustion will remain important in all future energy scenarios I have discussed, even when net zero emissions have been reached. So it will be still a very important research field. I also made the point that this might be especially the industrial energy demand will be important for us as a community. Many of us work in the fields of internal combustion engine, mobility, gas turbine, power generation. Not so many work in this field, and I think this will be more important in the future. I made the point that we need to try to combine experiment and DNS better, and also that machine learning approaches are a great opportunity, particularly in cases where modeling aspects are very challenging, and also if we can combine them in the right way with physics-based modeling, how we use large language models for chemical mechanism development I didn't get the time to talk about, but it's in the paper. And I try to share my own excitement here for lean pre-mixed hydrogen flames. And I try to make these 2 points, or especially this point. The theory is very important. Sometimes we can compute a case very, very quickly, but it doesn't tell us very much. And but the theory really informs how modeling needs to be done. So theory keeps being very, very important. And I try to show some examples for how we combine physics-based and machine learning models to arrive at these hybrid models. And then at the end here, let me just acknowledge some people, all my current and former doctoral students and postdocs who have in some way or another contributed to this work. The too many to list, but 2 I should actually mention is Lukas Berger and Antonio Artilli, because they have done a lot of this work here for hydrogen. All these people here helped me put the manuscript, helped me with the manuscript, and I want to take the opportunity also to thank the many collaborators we had over the years that worked with us on hydrogen, carbon-based fuels, simulation, machine learning, and many other aspects. Also too many to list them here. Finally, let me acknowledge the sponsors, and with this I'll stop, and thank you for your attention.
Thank you very much for an absolutely enlightening talk.
Thank
you. You've made us navigate from the application and the future challenges, through the fundamentals and into the extraordinarily innovative use of state-of-the-art tools. And we really appreciate that. So unfortunately, we are running out of time. So Bassam and I would like to hand you the certificate.
Fantastic. Thank you. Oui? Yeah, thanks.